Now we're ready for Chapter 5. Chapter 5 is the section on work and energy. So what we've seen so far, again, we've put together each step of the way. We've started off with understanding our dimensions, our dimensional analysis, the units, the standards. We've taken a look at some of the graphical methods. We've gone through a couple of chapters now where we've looked at building things motion in one direction and then motion in two directions. And we did that based upon understanding some fundamental concepts: distance and displacement, speed and velocity, and acceleration, the acceleration of gravity depending on the direction. And then we looked at understanding force and using force relationships in a static environment, and then a little bit in the motion environment. And so as we've done this, we've moved stepwise through the process of building on each of these concepts. So the next concept to understand is that of work and energy. So we have to look at defining what work is and what energy is, the types of work and energy that we're going to look at, kinetic and potential. We have to understand what kind of forces are involved in doing this type of analysis that adds to, takes away, or does nothing to the analysis. So conservative and non-conservative forces, conservation of mechanical energy, non-conservative forces, and the work kinetic energy formula, and then conservation of energy in general. And then we're going to add a unit to it, and we'll come up with power. So our definitions then are initially going to start off with building our understanding of kinetic energy and potential energy. So we are going to define kinetic energy as the energy associated with motion. So whenever you see a problem that you're looking at and it has to do with a motion portion, that's kinetic energy. If we're looking at something that is not moving, then we have the potential energy, and it is based upon its position in space. And you're going to understand this as we move through it. So let's look at a definition of work. We always start off with what defines each of these new units. So our definition of work has to do with moving something in the plane of interest, or in the direction of interest. So in this case, since we've started off with X so many times, we're going to look at the horizontal. So in moving this box across a plane in the horizontal direction, we are going to define work as that force times the cosine of theta times the distance. So it's force through distance, or force times distance. And if we look at this pictorial here, you can see if we've got a rope pulling up on this box and the force is at say between 30 and 45 degrees, then the work associated with it is going to be based upon that angle, cosine theta, and then multiplying it times the distance that we move the box. So the work W done by an agent exerting a constant force is defined as the product of the component of the force along the direction. That's key. The force along the direction of displacement and the magnitude of the displacement. The work done by a force is zero when the force is perpendicular to the displacement. So if the angle theta happened to be 90 degrees in this case, then the work is zero because, and you should be learning this by now, the cosine of 90 degrees is zero. So why is that so? Well, because it's zero because we're not interested in lifting the box. We're interested in moving the box in the X direction. If we were interested in the work of moving the box in the Y direction, lifting, then that changes the problem and work then becomes a factor. So we can see here with this bucket example, the work done by a force is 0 when the force is perpendicular to the displacement. So if the angle theta is 90 degrees, then the work is 0 because the cosine of 90 is 0. The sign of the work depends upon the direction of the force relative to the displacement, delta x. Work is positive when the component F cosine theta is in the same direction as the displacement. Work is negative when the component force cosine theta is in the opposite direction as the displacement. So if the applied force acts along the direction of the displacement, then theta is equal to 0 because there's no angle being made, and the cosine of theta 0 is 1. You have everything there. You've got unity with it. Okay? So that definition, work is equal to force cosine theta times the distance, is equal to force times distance, because in this case we're talking about the angle being 0. So if we look at some units of work in two common measurement systems, the SI and the US customary, in the SI units, which is primarily what we deal with unless we have some unique problem where we're trying to do a conversion, the system for the unit of work is a Newton meter. Well, that makes sense. Force is a Newton. The distance is a meter. Force cosine theta times delta x, Newton meter. And we can give that a combined name as a joule. So work is defined as a joule. You can call it a Newton meter, and in some cases you may need to, because when you decompose a problem, you may need to decompose it back. You may need to take newtons and decompose it all the way back to what? A kilogram meter per second squared. That was how we built the Newton. So in US customary, we call it a foot-pound, and the combined unit then is the foot-pound. Okay, so 1 joule is equal to 10 to the 7th ergs. Okay, ergs changes us from meters to centimeters. So let's take a quick look at a problem here. A man cleaning his apartment pulls a canister vacuum with a force magnitude of 50 newtons at an angle of 30 degrees. He moves the vacuum cleaner a distance of 3 meters. Calculate the work done by the 50 Newton force. So as we set it up, we can look at our kind of free body diagram here. We've got a y direction set of forces, the normal, and mg, the weight. And we've got the force that's going on in the x direction at an angle of 30 degrees, force of 50 newtons. So since we are given these values, force as 50 newtons, theta 30 degrees, delta x, or the displacement 3 meters. Stick it in the relationship. Work is equal to force cosine theta times delta x. We have 50 newtons times the cosine of 30 degrees times 3 meters. And we get then work as 130 Newton meters, which we can call 130 joules. Again, as I said, we could call this 130 kilogram meters per second squared times meters, which would become kilogram meters squared per second squared. So now let's change the geometry a little bit. Now we want to find the work done on the vacuum cleaner by the man. Okay, this is the work being done on the vacuum cleaner as the man pulls it 3 meters, but now he's pulling the hose straight parallel to the ground. So now we have no angle. So the force is still in 50 newtons. The angle now is 0, but the distance is still 3 meters. We run it through the same relationship, force cosine theta times delta x, 50 newtons times cosine now of 0 degrees, 3 meters. So now in doing so, the cosine of theta, you might want to write these down instead of plugging them into your calculator every time. Cosine theta is 1. So we have 50 newtons times 1 times the distance, 3 meters, and we get 150 joules. Now, If we go back, let's go back. We were at 130 joules. Why? Because our force cosine theta had a component of x that only let it be a cosine of theta amount. Now we've got the full measure of force times 1 cosine of theta in the problem. Okay? So when we come back, we're going to start adding some of these kinetic energy relationships. Yes, we're going back to motion equations. You know, you're going to be plagued with motion equations for the next, what have we got left? 11 weeks, 12 weeks. You're going to see them again. So when we come back, kinetic energy and the work kinetic energy theorem.